Okay, we'll see. So what is this lecture about? I'll start with giving you an overview of what's going to happen in this semester. And then we will start talking some actual science, okay? So in a nutshell, the lecture is about learning to make structured predictions. And I will comment on each of these words. By the way, I will, after the lecture, I will make my handwritten notes available as a PDF, but I would really encourage you to try and take notes yourselves, both because you may understand your notes better than mine, and because it actually helps, in my opinion, the learning process if you have written the important stuff as opposed to just seen it, or at least for some people that works. And finally, it's not a bad exercise to try and take notes all the while following a concept, but it's up to you. Okay, good. So it's about learning to make structured predictions, and I'm going to show you a data set or a video of a data set, and then comment on different kinds of questions you can ask from it. So we here see a microscopic data set acquired by Rappaport et al. The original data was just gray value, so the colors already show you the result of some processing that we've done here. And this type of data is interesting for people who develop drugs, for example. Yeah? So you can look at time-lapse movies from bacteria or from cell cultures, and then you can ask questions like, if I give this drug or that drug, how does it influence the behavior of the cells? If it's bacteria, how many does it kill? Which does it kill? How does it change the dynamics of the colony? And so on. So this is the kind of question an end user may ask. But in terms of intermediate steps, there are different levels of detail or different kinds of questions that you can ask. And when I say structured prediction, I mean that we feed in the video and then we get out some kind of analysis or some kind of result which is more or less structured. And I give you a range of such possible outputs. So, for example, I can talk about structured prediction. My handwriting, is never nice in general. But of course, I blame it on this digitizer, yeah? But anyway, when you cannot read something, please let me know. So structured prediction in the wide sense, I start with this. In our case here, this could be, for example, a foreground-background segmentation. Segmentation means that we assign each pixel, in this case, to one of two classes. And for example, the possible outcome could be, if I have two overlapping lengthy bacteria, then I could call this the foreground, and everything outside would be the background. Now, if we make this a decision pixel by pixel, it is typically going to be very noisy. So I will have isolated foreground pixels and isolated background pixels in the middle of the foreground. And this is why it makes sense to couple these predictions. And coupling these predictions, this is what is meant when we say, or this is one of the things that can be meant when we say structured prediction. So the interaction here could be, for example, interaction between the predictions at neighboring pixels. then we can ask more complicated questions. For example, we can say, I'm not just interested in what is bacteria or not bacteria. I can be interested in where is bacterium 1 and where is bacterium 2 and which pixel belong to which. So this problem is called instance segmentation. And here, for example, if we assume that these beasts can crawl over each other, I'm not sure bacteria can do that in a dish, but let's do that here for the sake of argument. Then I would, for example, say that this is bacteria number 1, and this here is bacteria number 2. So I explicitly delineate. Or, to give you another example, assuming bacteria cannot crawl across each other, let's say this would be the situation in the foreground-background segmentation, and in the instance segmentation, even though they overlap, I would like to say that actually this is 1 and this is 2, even though my microscope cannot cleanly resolve them. So in the first case, the interaction has been purely local. So I can say this is local interaction between predictions and adjacent pixels. In instance segmentation, depending on how I ask the question, I will have some non-local interaction. For example, I can say that I want to use each name or each index for a bacterium just once across the whole image. And then if I'm calling this one number 1, then I'm not allowed to call any other bacterium in the same image also number 1. And that would be an example of some non-local interaction. And then finally, at an even higher level of abstraction, I can ask for the lineage tree. In German, Ahnenbaum or Stammbaum. So here I could say, please, for a video across time, starting my colony with just a single bacterium, tell me when it divided and when its children had children, and then maybe some of these children have died out, but others have kept multiplying, some did not multiply, and so on. Okay, so this would be an example of a lineage tree. And here when I call this more structured because if I get a movie with n pixels, then in the case of the foreground-background segmentation, I also make n predictions, one for each pixel in my movie. But on the other hand, in this last case here, when my input movie has n pixels, I don't know in advance what this lineage tree will look like. So I don't know how often the bacteria are going to split, how many branches this tree will have, how many nodes the tree will have. Also, there's no primitive or no naive one-to-one mapping between pixels in my video and nodes in the tree. So there is a significant amount of structure here. When my desired output is, like in this case, an attributed graph. So here, output is a tree whose topology is previously unknown, or let's say whose structure is previously unknown. Let's say I can impose the prior knowledge that it should be a tree, so that these organisms never merge, that they can only divide or die or move in and out of the field of view. But like I said, I don't know how many branches, etc. it's going to have. Okay, and this is what I would call an example of structured prediction in the narrow sense. In the narrow sense. So you see we've spanned, or I've spanned the possibilities from unstructured or from little structure to a lot of structure. And I am mostly interested in my own research in this example of having predictions with a lot of structure, simply because some meaningful questions require such answers with a lot of structure, and also because it's the most challenging and hence interesting problem algorithmically. Yeah? Why is it so challenging? Because up here in this kind of predictions with little structure, plain convolutional neural networks do great. So I'm writing CNN here as abbreviation for convolutional neural network. And these convolutional neural networks, they have undergone tremendous development and have seen great progress in the last 5 years. And this is often the only thing that people want to know about, because it's so successful in some applications that previously were very difficult to solve. However, when we start going to more structured predictions, like the instance segmentation, then plain convolutional neural networks have difficulty here. And this is roughly where the research stands today. Yeah? So let's say this kind of plain problem was solved around 2010 or so. Here, the community is working on it in 2017. So maybe let's say that in 2020, this will be all done. And this thing down here, well, some people are thinking about it, but it's completely, I would call this an unsolved problem. So standard feed-forward neural networks or multi-layer perceptrons without any kind of post-processing cannot produce this kind of output yet. And you can always hook on some post-processing, but it's much nicer if it's really integrated into the method, and that's not really the case yet. Okay, so this is also, maybe you hear that I'm being a little bit defensive here, because neural networks are really the single most successful tool you have nowadays. And as a consequence, like I've said, it's the only thing that many students ever want to learn about at all. Because they think this will be enough to solve some problems, or it will be enough to get a job in finance or in some social network company. But I believe, and I might be wrong, but I believe that they will not take us the full way, and that other techniques are required. And in this course, I want to give you the foundations for some of these other techniques, and bring you, that's an overall aim of the research of this course here, bring you close to the frontier of research in certain select areas or sub-problems. Okay. Now further up, I said that this course is about learning to make structured predictions. What does learning mean? It means that we want to infer good prediction rules or train good prediction systems from some ground truth example. So when I say learning to make structured predictions, what I mean is infer useful rules, where useful means ones that generalize well. from annotated ground truth examples. So ground truth is a technical term. Good. And now comes a terrible diagram, which will give you an overview of everything that we will, or almost everything that we'll be doing in this course. And there will be many words and some, that will not be meaningful at this point. But if they will be meaningful at the end of the semester, I will claim this is success. Okay. So bear with me for a moment while I, try and write and then explain. So fundamentally, we are going to look at the loss incurred if the correct output for some input xi is t of xi, and my prediction is z of xi, and any method which I use to make predictions will have parameters that I need to learn. Okay, so xi would be some input. In this course, because it's machine learning for computer vision, the input will be an image or a video, something like that. T here is the ground truth. And I'm not specifying in this pretty abstract formula, which will become bigger, if this ground truth is a graph or if it's a pixel labeling or what it is. Okay, it's just the desired output. It's what my system should give out when I input the ith input here, xi. Then I have a prediction. My prediction will hopefully be a function of the input. Otherwise, it's a pretty boring predictor. And it will make this prediction based on parameters. So any rule will have, like thresholds or something in there, some numbers in there. And if these numbers are chosen well, then I might make good predictions, or I might not. If the numbers are chosen poorly, I will certainly not make good predictions. Okay, now the empirical loss means that I have a training set. Let's say I have a total of n training examples, and my goal in training is to minimize the average loss when going over all my training examples. Also, I have not yet said what the loss is. This will, of course, depend on the nature of z and t. Yeah, so if z and t are both graphs, then the loss could be some graph matching distance. If z and t are just a single number, it could be the difference between the two numbers or the absolute difference between the two numbers, and so on. Yeah, so what the loss exactly is will depend on the nature of the output here. And now comes the training itself. I want to find good parameters which minimize this thing. Yeah, so I'm writing argmin here. I want to find those parameters theta that minimize the expression on the right-hand side. So this minimizes the empirical loss on the training set. But what can be the problem if I only consider the loss on the training set? You know that, or you may know that problem, if you do something like a polynomial fit to your observations or something, what can happen if you only observe the quality of fit? You can overfit. So we need to somehow guard against the overfitting. And to this end, we typically take into account not just the empirical loss on the training set, but also some regularizer, which I'm here abbreviating with a capital omega, and that's a function of the parameters. Regularizer is also a technical term. It means it's something that I think will be useful to help me avoid overfitting. Okay, Now, the formula has been so generic that I have many choices for any of these things. For what predictor do I use, what loss function do I use, what regularizer do I use, and how do I perform the minimization. And during this lecture, we will look at some of the ingredients here and study relevant techniques. Yeah? So one prediction that I could use here is, try and get away with just using a neural network. This neural network will take some input xi, and it will have some parameters. And if it's a feed-forward neural network, this is just some nonlinear function of my input. However, sometimes when I want to model interactions, or if I want to model prior knowledge on my problem domain explicitly, such a feed-forward neural network is not going to be enough. I need more. And something that has been used with great success is to define an energy function. An energy function which depends on the output, or this assigns, so given an input xi, this assigns an energy to every conceivable output zi, and this energy function will be parameterized by my parameters theta. And now an energy function is not a prediction yet. So if I want to get out a prediction, I typically choose the zi, which gives me the lowest energy. So I use as prediction the z which minimizes this energy function here. And now note that this makes the whole equation more interesting, because now I have nested minimization problems. So during training, I want to find my best parameters theta, which minimize the empirical loss. But each prediction will in itself be the result of an optimization process. Interesting, but also complicated. Now, if I write energy function, where do I get such an energy function from? And as I will soon illustrate, it is a good idea to compose this energy function out of as a sum of local interactions. And this is often in terms of undirected probabilistic graphical models. So I'm writing only UGM for now, and I will write it out later. Undirected probabilistic graphical model. And in the course of the semester, we will look at two variants of this, namely graphical models which are defined over discrete random variables, I could also call this a discrete Markov random field, and then undirected graphical models which are defined over continuous random variables. In fact, we will only look at a specific type, namely, we will only look at Gaussian distributed variables here. So this will be a Gaussian Markov random field. And depending on whether I use a discrete or a continuous model here, the optimization process is also going to be different. So if indeed I use a Gaussian Markov random field, then this minimization process here amounts to solving a linear system of equations. I'm abbreviating this for now with a linear system of equations, LSE. And on the other hand, if we have a discrete Markov random field, we will usually have harder optimization problems here. And one way to formulate and then solve such harder optimization problems is in terms of integer linear programming. So some people have come to the class later. Who knows about integer linear programming? Okay. So you will, don't worry if you don't know the terms now. I promise you will understand in 2 weeks' time. And integer linear programs are very expensive to solve in general. So sometimes the problem have a benevolent structure, and that means that we can simply use dynamic programming to find the optimum solution. So we can use dynamic programming to solve this argmin over Z problem. Who has heard about dynamic programming before? Hey, the computer scientists, come on. Some people said they do scientific computing. Okay.
There's only one lecture
Okay. Good. So here are, the keywords of some of the things that we will do. And now here's our trajectory. We will not start with the neural networks, but we will start with discussing undirected graphical models as a means to make predictions. We will start with discrete graphical models. We will look at integer linear program as a general solution strategy. We will then look at dynamic programming as a variant. You don't need to copy the screen line, okay? I'm just giving you the outline here. We will then look at dynamic programming as a special case that works if the model has a benevolent structure. And then we will look at continuous Markov random fields and how they can be solved before turning to neural networks and discussing how neural networks can be optimized, so how to find the parameters theta. For that, we will also need regularizers. And at this point, we have all the basic building blocks and can come to the really interesting part, namely here, how to merge neural networks with probabilistic graphical models. And at the very end of the semester, we will probably talk about reinforcement learning, but I might change that. In reinforcement learning, we have only very weak supervision, so we don't get to hear what is the correct solution. We just get penalized every time we make a wrong prediction, but we don't know, at which point we were wrong. So this is very weak supervision, but because it's weak supervision, it's also interesting if you can master to learn in such a difficult scenario. So overall, I will try in this lecture course to teach you the difficult things, or mostly the difficult things, because the easy ones, like a particular neural network architecture, you can very easily read up by yourself. And studying in general is your best chance in life to learn the hard stuff. Later in life, I know it because I look at myself, I look at many people, it's very difficult to find the time to learn the hard stuff. Okay, so that's the good news and the bad news. Huh? Okay, do you have any questions? So far? Yes.
Will this course more focusing on the theoretical stuff or practical stuff? For example, the graphical model.
Will we focus more on theoretical, more on practical? The lecture will be theoretical, and in the exercises you will get a chance to really try it out on concrete problems. But overall, no. Judging, so according to a mathematician standard, this would not be a theoretical course because I'm not going to have proofs and lemmata.
So there will be no proof.
There will be no proofs. You will not be asked to, write proofs in your homework. On the other hand, by computer vision standards, I would say this is going to be a theoretical course, because many people, or much of the work in computer vision is about building pipelines and is very empirical. And by those standards, I would say it's a theoretical course. Okay. Now the answer is it depends.
Why are we using only dynamical programming for the integer programs?
Oh, just because we only have like 14 weeks. So there are certain types of graphical models which have structure that affords faster solvers, like by means of linear programming or something. It's just that I could spend an entire semester only discussing efficient solvers, and I want to cover some of the other stuff. There is a course, or there will be a course by Bogdan Savchinsky, and if you're interested in hearing more about different solvers for